In the previous video, we looked at how we can execute another program from within a process. And we realized that when we do so, that program takes over this process. And in fact, we never even get to any point after this exec call if it's a successful call. So what is the context of the program we were executing? Well, we're going to continue the same demo command that we were looking at before forward. So we're going to be executing the grep program, and we're using regular expressions, the extended syntax. We're going to match any lines that end in AC, and we're going to match from or read from standard input. Right? So if we think about what we're going to be focused on this lecture is input redirection. Okay, so if I run this program like normal, my input is coming from standard input, right? And I type hello.c, and we see that my output is also going to standard output, and that's connected to my terminal. What we learned in a previous video is that if we redirect, actually before we talk about redirection, let's just very quickly sketch out our understanding of how this is all connected together. So we know that our operating system has an IO table, or technically called a file table. And there's going to be an entry in it for the terminal, and the terminal is what we're typing into and out of. Right? Any open files that we do or that we have on our file system will also be here as well. I'm just going to put in quotes IO because really I think thinking about this as any place where we can send and receive data to and from is a little bit easier to understand than thinking of this just as files, even though technically it's called a file table. And our process has a file descriptor table. And this is its own namespace where it's got some integers. So 0 is standard in. And it's going to be connected to some entry in the operating systems table, right? So we have a level of indirection here. And because we are beginning our program, in this case a.out, from the context of a shell, standard input is connected to our terminal. Turns out standard output is also connected to our terminal, and standard error. Right? And so anything we read or write is going to be coming from or going to our terminal. Okay, and I'll just write terminal out here. Okay, so what happens when we use redirection? So just to remind ourselves of this really quickly, if I run this program /a.out and I redirect to a file standardout.txt, this sets up redirection such that standard output is going to a file. I write hello.c, and we don't see any output on our screen, even though we know that this matched the pattern we were looking for. I could also do foo.c just to prove to ourselves that the contents that we just typed in are actually being redirected to the file that we just set up, named standardout.txt. So if I list my files and open up standardout.txt, we see sure enough those two matches were there. Right? Now, something curious is happening here. Now that we know a little bit about how exec works, we can convince ourselves that there must be a clever handoff happening here, right? So how is it that even though we have nothing in our program, we have nothing in our exec.c program that says, hey, if there's redirection happening, you should do something special about that, right? It just worked. So let's remind ourselves what happens when we redirect output. So what happens is there's going to be a new file set up. So I'm going to name this f0, and that file is standardout.txt, right? So this is just the name of a file. And when we use this redirection, we're saying a.out's output is not going to be sent to the terminal. It's going to be sent to this f0 entry instead, right? And I should make those errors a little bit more clear now that we have two entries in our table. All right. So now our connections look like this, right? When our program outputs the standard output, it's connected to this file standardout.txt, and that's what's sending the output to it rather than back to our terminal for us to see. So what we should notice here and pause to just appreciate is that this is working, even though the program that we're running actually is grep, right? So we're saying start up this a.out process, right? And then go on and redirect its output to standardoutput.txt. But this program is actually replacing itself using the exec call with grep, right? And so somehow these connections are maintained. And the good news here is that this is a pretty clever and hopefully pretty straightforward, once it's explained, idea that, well, it actually makes sense for us if we run the exec function to keep whatever file descriptors were set up, to duplicate those and have them carried forward to the next process that's running. So unlike all of the memory that got replaced for like the stack and the heap, the static memory, the code itself for the program, the process's file descriptor table is actually carried forward. And that's what allows this redirection to still be maintained, right? Well, if we can redirect output using the bash command line like this, then we should be able to do so in code. And let's actually take a look at how we can make this work in code as well. Right? So that's us performing the redirection from the command line shell, from our bash shell. All right, but let's go back into exec.c and think about where we're at. Right? Okay, so I've resized and added some space here so that the text of my program doesn't collide with my little drawing here. And I want to reset this drawing to how we think about this program starting to begin with. Like the way we were running this program before is everything is connected to a terminal, right? And there's no file 0 here. All right. So if we want to work with output redirection and think about how does output redirection actually work at the system call level if we wanted to go implement it ourselves without doing it at the shell. And in order to do so, we need another header file. So I'm going to include, we looked at this header file before, fcntl, which is the file control header file and contains some common operating system level functions for working with the file system. And the first thing we're going to do after we set up this binary file variable to hold the name grep, let's open up a file that we're going to redirect our output to. Right? So we looked at the open function call before, and it returns to us a file descriptor, which is going to be the integer in this process table. Right? So let's name this file descriptor. Let's say redirect fd is going to be the name of it, and I'm going to open. And the file that we're going to open, just to carry forward the example, actually let's name it something different. Previously in the shell, we redirected to standard output.txt. Let's name this file redirect fd.txt. And let's open this with a few options. These flags are, again, if you Google them, you will learn more about them. They're a little bit beyond the scope of this discussion, but effectively we're going to create the file redirect fd.txt if it doesn't yet exist. We're going to truncate the file if it does exist, meaning we're going to reset its contents back to scratch if it did exist and had contents in it already. And we're going to open this file up for writing only. Right? So let's talk about what this line of code is actually doing behind the scenes. Right? So this line, when we call open, it's causing the operating system to have a new entry, and I'm going to call this F0, and I'm going to name this redirect. I'm just going to it .txt, and it's being opened with these 3 options, right? So I'm not going to keep track of those options there, but imagine that those options are being kept track of at the operating system level as well. The other thing that happens is in our process, because we called this open function from within the process is reserving a new file descriptor that's going to be connected to F0, right? And so what we looked at before was if we were to write some data to this file descriptor 3, it would be written to that file, right? And this 3 value, and we're just presuming it's 3 because that's typically going to be the first available file descriptor, but it's just going to be some ID in the process's file descriptor that hasn't yet been used, would then be assigned to our redirect fd variable, right? So this variable now contains the number 3, which is this entry that connects us to this file that is maintained by the operating system. All right, so now what we would like to do, right? Well, what we would like to do is tell the program, hey, rather than standard out going to terminal, we want standard out to go to the F0, whatever F0 is, right? So we actually want to take what is in file descriptor entry 3 and write that over or duplicate that into the file descriptor for our standard out. Right? So it turns out there's a function in our Unix standard library or Unix standard library called dup2, right? And what dup2 does is it takes some file descriptor. So again, that's going to be like this number 3, and it says, hey, whatever it's connected to, whatever its data for its file descriptor is, duplicate that onto some other file descriptor. And in this case, we're going to duplicate that to stdout. So I could have done 1 here, but again, we like to avoid magic numbers. So I'm going to use stdout file no, right? And that is a constant defined in standard IO. Right? So we're saying connect this file descriptor, copy whatever entry it has, which was F0, into the descriptor for the standard output. All right, so let me try changing colors here and imagining this line of code, dup2, what's it doing? So it's saying take F0. Actually, let me back up. It's saying take the value that's in entry 3, right? Redirect FD is the value 3, and it's going to take the contents of its value and copy it to the entry for standard out, which was 1, right? So standard out is now going to be overwritten, and it's going to be connected to F0, right? And so what we've done here is we've duplicated the file descriptor contents in file descriptor 3 for this process to standard out. So now standard out is going to point to file 0, all right? So if we've done our job here, that means that we can assume that when exec goes to run, if we believe that this file descriptor table is going to be copied forward to grep, then its outputs should no longer be sent to terminal. They should be sent to this file that we opened up. Now, to be good citizens here, we should also close redirect FD before we hand off. Now, this close function call is kind of an interesting one. It's commonly confused that this close function call is actually closing this entire file entirely, such that we wouldn't be able to write to it at all. Why would you want to do that? We actually do want to write to it in grep. Well, what's actually happening is each time there's an entry in a process file descriptor to a given operating system file entry, a counter is incremented. So if we imagine how many references were there to the terminal counter, there are 2. How many references are there to this file entry 0? Currently there's 2 for these 2 file descriptors. Well, if we say that we're going to close this file descriptor 3, what we're saying is actually bring this reference count back down to 1 and make this file descriptor 3 available for use for some other file descriptor if the process wanted to open something else. So it's as if we make that go away. And by closing that, we now clean up the process table just before we hand off control to grep, right? Now, the last thing I'll mention is that these system call functions here also have error states, right? These aren't guaranteed to work. And if you're actually using these in a real program, you definitely should check for error conditions and do error handling. This is just trying to demonstrate what's going on at a conceptual level when everything is rosy. But you should never assume that everything is going to be rosy when you're writing system code. All right, so let's try this out. So we're back in the terminal and we need to recompile our program. So gcc exec.c and /a.out. All right, so now we try foo.c, and notice that output, that this is a matching line. It ends in C. It's not sent to our terminal because in our program, we by hand hooked up output to go to a file, right? And I try another file like hello.c and moo.c, and then control D to end input. Now, if I list my files, notice that we've created this redirect FD file. And if I were to open it, we see that those contents were there. So what we effectively did was, let me actually open up my code one more time here. So I'm going to open up exec.c. What happened was we set up this redirection ourselves manually. And so if we're going to implement a shell, the shell is also going to be doing this. In fact, whenever you run a command with redirection, the bash program behind the scenes has some code that looks something like this for hooking up for opening a writable file at the operating system level and then overwriting standard output of the process that it's setting up to be headed in that direction instead of to the terminal, right? So we opened up a file, and that created a new file descriptor we named redirectfd. We duplicated that. We overwrote standard out with that file descriptor, and then we closed it just to be good citizens, right? And so this is how we can manually implement file redirection. And what I want to just close with is a little bit of discussion around this dup2 function. Right? So this is the important one in this particular video. Notice that we had some file descriptor, and we were able to say, okay, we've opened up a file that was previously file descriptor 3 connected to F0. We can copy over standard out in this way. If we wanted to say standard error should actually be sent to file 0, we could have done the same thing, right? And we could have actually sent both standard output and standard error to this example file. If we had another line that was something such as this, right? We could have said duplicate the file descriptor for redirectfd onto standard error, right? And so this would have sent output from both standard output and standard error to the file that we're redirecting to, and would have resulted in a diagram that looks something like this, right? We can say F0 is no longer connected to the terminal, but is now connected to file 0. If we had opened a file for reading, right, so we would have needed to use different options here, but if we had a file that we already wanted to read from, we could have opened it for reading and reconnected using this dup2 function call, or rewritten its file descriptor to come from that file rather than from our terminal, and that's how input redirection would work, right? And so this dup2 function call is important for configuring a process's file descriptor table. And so this is how we're reconnecting things and able to make new connections or change the connections of standard input, output, and error before we go and execute some other program. And because when we go and execute that program, this table gets inherited by the new program that runs, we can form those connections for the program to run before it gets going. And that will wind up being something that's very key in our shell for making piping work as well as output-input redirection.